this video, we're going to talk about continuity, and that's going to help get us started to think about derivatives. So if we take a look at this example where we are going to park at a parking meter, and it only accepts quarters, and that's all it's going to accept. This is back in the day, and each quarter will give you 15 minutes of parking. So if we were to graph our time versus cost for the first 15 minutes, that it's going to cost 25 cents to get 15 minutes. The second quarter I put in is going to give me an additional 30 minutes. So I have 30 minutes of parking, but it's going to cost me 50 cents. And then if I put in 3 quarters, it'll give me 45 minutes of parking. And so for 3 quarters, I will get this 15 minutes of parking. For the second quarter, I have this minutes of parking, and then for the first quarter, I have this many minutes of parking. Now I can see, looking at this graph, that my domain is from 0 to infinity, but my range has got gaps in my graph. So we have gaps in the graph. That's, when we look at this is a step function, and we can see it's not continuous. And now we're going to define what continuous means. So for a function to be continuous, there are 3 things that must happen. The first one, it has to be defined at a, where a is in the domain of your function. The limit as x approaches a of f of x has to exist. That means there can't be any jumps. And then the limit as x approaches a of f of x must equal f of a. If this fails, any one of these 3 fail, then we're going to say it's discontinuous at a point A. If one of these fail, not all of them have to fail, only one has to fail. So if it's not defined, or the limit doesn't exist, or the limit does not equal the function as you evaluated at A, then we say it is discontinuous. So there are 3 types of discontinuity. The first type is a removable discontinuity. That's when you have a hole in the graph. So that is a removable discontinuity, like this one, or even this one. So this one does not have, it is not defined at 1. The limit exists, so as this example here, the limit exists at 1, but it's discontinuous because f of 1 does not exist. If we take a look at x equals 2 here, this is what we call a removable discontinuity still. The limit exists. F of a, or f of 2 in this case, exists, but these are not the same, so it's discontinuous, and it's a removable because it has a hole. At 3, we fail at the fact that the limit does not exist, because this is a jump discontinuity. You pick up your pencil and you have to jump to the next piece. So this is a jump discontinuity because you're physically jumping in the graph. The condition that fails for 3 is the fact that 3 is defined, f of 3 is defined, but the limit does not exist. So that's one of the things. And the other thing is the limit, obviously because it does not exist, does not equal f of 3. The next kind is the infinite discontinuity, which means that we're going to infinity. Notice how on the left side of 5, I go to positive infinity. On the right side of 5, I go to positive infinity. So we call this an infinite discontinuity because the graph goes to infinity. So if f of x is discontinuous at a, then either we have a removable discontinuity because even though the limit exists, that f of a does not equal L. We have a jump discontinuity when the limit does not exist. This is how we're going to define the jump discontinuity. As the limit as I approach x, or a from the left and a from the right, exists, but they are not the same value. And then the infinite discontinuity is by definition, as x approaches a from the left, it equals positive or negative infinity, or if as x approaches a from the right, it is equal to positive and negative infinity. It does not necessarily have to equal the same thing. They can go in different directions for it to be an infinite discontinuity. What has to happen by definition as x approaches a from the left, or as x approaches a from the right, that it goes to positive or negative infinity. So to determine the type of continuity or discontinuity is the first thing you're going to do is make sure that f of a is defined. So can you put in that number you were taking at the limit as x approaches? Can you put it in there, and does it give you a number, or is it undefined? If it's undefined, you're done. You don't have to go any further. You don't have to check anything. You're done. If it is defined, then you have to go to the next step, and that is to determine if the limit exists. So if the limit does not exist, but it is defined, then you're done. But if the limit exists and it's defined at a, then your next step is to determine whether or not the limit as x approaches a of f of x equals f of a. If it doesn't, you're done. If it does, then it is continuous. So all three of them have to be satisfied for it to be continuous. So as we take a look at our first example here, what we want to do is determine if it's continuous at a. And if it's not continuous a, can we determine what kind of discontinuity? So for this, a is 3. Now we know in the function g of x is equal to 1 over x minus 3 that the domain is all values with the exception of 3. So we know it's discontinuous because when we think about the limits is that f of a must exist. So that's the first one. F of a must exist, and this is where we fail. So we don't even have to go any further. F of a does not exist. So it fails on the very first check. And in particular, we know that since it is a restriction in the domain and the way we define the vertical asymptote, that it is an infinite discontinuity for A. Let's take a look at B. Again, A is 3. So if f of x equals 3, then it's 2. If f of x does not equal 3, then we use this equation. So the first part of the checklist is f of a must exist. Done. The second one is the limit as x approaches a of f of x exists. So if I take a look at my function here, I have f of x, and I'm just going to look at the first piece, the top piece. I'm going to factor this into x minus 3, x plus 2, or x plus 1, x minus 1 I mean. So x minus 1 is what it factors into, all over x minus 3. These cancel, and I'm left with x minus 1. Now there is a hole in the graph. So the hole in the graph is at 3, and we're trying to decide whether or not we fail some of the limit laws. So if I do the limit, then as x approaches 2 of f of x, this is equal to the limit as x approaches 2 of x minus 1. Now I know that I can go ahead and do a direct substitution. So I do a direct substitution and I get 1. So we know that the limit exists. Now, the last piece is we need to confirm the third part of continuity is the limit as x approaches a of f of x must equal f of a. Now when I did the limit, I got 1. But if I go back up here to my piecewise function, my original piecewise function, at x equals 2, it is 3. So what I am checking now is the limit as x approaches 2 of f of x. It does not equal f of 2, or excuse me, f of 3, because f of 3 is 2, but the limit as x approaches 2 is 1. So this is where it fails. And this is a removable discontinuity because it doesn't jump. There is just a hole in the graph that is defined but not at. F of a does not equal the limit as x approaches 2 of f of x. So let's take a look at our theorem here, 2.8. Theorem 2.8 says, all polynomials and rational functions are continuous on their domains. So if we take a look at both of these, so g of x is a rational function. It is continuous on its domain. Its domain is everything but 3. So yes, g of x is equal to 1 over x plus 3 is continuous for everywhere except for 3. And polynomials are continuous everywhere on their domain. The definition of continuity on an interval says that a function f is continuous on the interval I if it is continuous on all points within that interval I. If I contains its endpoints, continuity in I means that it's continuous from the left or the right at the endpoints. So what I mean by that is, let's take a look at this graph. So here's my graph. I'm going to call this -3, and I'm going to call this 4. So the interval I'm looking at is -3 to 4. So if I contains the endpoints, well, in this case, it only contains the endpoint -3. So it is continuous, it is right continuous, because I'm coming in from the right. I am right continuous at x equals -3, and that's because it's inclusive. I am not left continuous at x is equal to 4 because it's not included. It's an open circle, it is not included, so it is not left continuous at 4 because it's not included in the interval. So just like with limits, we have the left limit and right limit, we have the left continuity and we have the right continuity. So if we take a look at this particular graph, it is a piecewise function. It is continuous on -∞ to 0, and that's because 0 is included. And because 0 is included, it is left continuous at 0. It is continuous on the open interval from 0 to infinity, but it is not right continuous at x is equal to 0 because it's not inclusive. That point is not inclusive on that part of the interval. So we say it is continuous on 0 non-inclusive to infinity. So that gets us to how we define left and right continuity. So f of x is said to be continuous from the right if, as x approaches a from the right, f of x equals f of a. We say f of x is left continuous or continuous from the left at a if the limit as x approaches a from the left of f of x is equal to a. And you can see from our example up here that this is not right continuous because f of 0 is not that point there. So then we have continuity of functions with roots. Assume that m and n are positive integers with no common factors. If m is an odd integer, then the function f of x raised to the n over m is continuous on all points. So in other words, if I'm taking the cube root of something, the cube root is continuous on all points in which f is continuous itself. If m is even, so in other words, I'm taking like the square root, it's continuous at all points of a in which f is continuous for f of a greater than or equal to 0. Let's just take a quick look. If I had f of x is equal to the cube root of x minus 3, that since m is even, it is the cube root, so that means it is continuous on its domain, which is -∞ to infinity. But if I said g of x is equal to the square root of x minus 3, and then it's continuous on its domain, which is from 3 to infinity. Anything on the left side of 3 is not defined, and so I have continuity on 3 inclusive to infinity, and I have a right continuity, continuous from the right. If a continuous function has an inverse on an open interval, then its inverse is also continuous. So let's think about what we have for exponentials. So here's my exponential. Here is f of x is equal to b raised to the x. That's my function, and we know that this is an exponential. It's continuous on its domain from negative infinity to infinity. The inverse of b of x is the log based b of x. We'll call this we'll call this f inverse of x. So that is the inverse. So our function, my exponential function b to the x, is continuous on its domain, which is from negative infinity to infinity. On my inverse, it is also continuous from its domain, which is non-inclusive 0 to infinity. So these are inverses of each other. This is continuous, and so its inverse is continuous on its domains. Continuity of trig functions. Trig functions are continuous on their domains. So sine x, cosine x, the sine x, the inverse is sine inverse. Cosine is cosine inverse. Tangent, tangent inverse. Cotangent, cotangent inverse. Secant, secant inverse. Cosecant, cosecant inverse. And that is, of course, on the domains. So think about where we have the domains for the trig functions and their inverses. So now we're going to determine the values of x in which the function is continuous. If there is an x value in which the function is discontinuous, determine that type of discontinuity. So we have to check for all 3 things for continuity. First is f of x, or f of a exists. So that's the first one. So f of a exists. So as I take a look at this first example, my domain, because it's a polynomial, is negative infinity to infinity. So it is going to be continuous on its domain. It's going to exist everywhere. That means that the limit, that's the other thing you have to check, is as x approaches a, of f of x exists. And for the first example of the polynomial, the limit will exist everywhere on its domain. And then the third one is the limit as x approaches a of f of x has to equal f of a. Now for the polynomial a, this is going to be continuous everywhere on its domain. So this one is continuous everywhere. So that's my answer here, is continuous everywhere. For g, my domain is everything with the exception of x cannot equal -1. So on its domain, f of a will exist as long as a is not -1. The limit as x approaches a of f of x will exist as long as a is not 1. And then the limit as x approaches a of f of x will equal f of a provided a is not 1. So my moment of discontinuity is that x equals -1 is discontinuous. And it's an infinite discontinuity. Okay, so taking a look at C, the domain for C is x such that x does not equal -1. And on its domain, f of a will exist. The limit of f of a of f of x will exist, and the limit will equal the limit as x approaches a of f of x will equal f of a on its domain. The place of discontinuity is the same as up above. So this is discontinuity, and it's because it's an infinite discontinuity. As we take a look at D, this is the absolute value of x minus 2 over x minus 2. So we know the domain for this is x such that x does not equal 2. So for this, it is continuous everywhere on its domain. There's no place in which it's undefined. So the first part will be checked off. The second part is the limit exists on everywhere except for x minus a. Now, if you were to graph D, it's going to look something like this. That everything on the left side of negative or positive 2 is going to be below. It's going to have a hole there. Everything on the right side of 2 is going to be above, and it's going to be at the point. This is 1 and this one is negative 1. So that's what the graph is going to look like. So just looking at the graph, we know that on its domain we are continuous, where the point of discontinuity is at 2, and it's a jump discontinuity. So it is a discontinuous at x is equal to 2 is discontinuous. And the kind that we have is the jump discontinuity. But everywhere else, we're good to go. So with the last one, I'm again going to determine what my domain is before I do any algebraic cleanup. So x cannot equal 2. And then when we factor this, the numerator is going to factor into x minus 2, x squared plus 2x plus 4 over x minus 2. These cancel, and I am left with x squared plus 2x plus 4. Now this is continuous on its domain. The domain is everything but 2. So at x equals 2, we are discontinuous. And the type of discontinuity is a removable. So it is continuous everywhere except for at x equals 2, and it is a removable discontinuity. So if you were to graph it, it would look something like this. So it would look, move this up, move this up. There we go. Let me move this up. So it would look something like this. Here's my graph. And it would look something like this, but at 2, there would be a hole in the graph. So it's going to look something like that with a hole in the graph at 2. Let's take a look at f, and I'm trying to determine what is the domain for f. And to figure out the domain for f, I know that x to the 4th minus 1 has to be greater than or equal to 0. This goes back to some pre-calc 1 stuff. This factors into x squared minus 1 multiplied by x squared plus 1 has to be greater than 0. X minus 1, x plus 1, x squared plus 1 is greater than or equal to 0. Now we're going to do the sign chart where I've got x squared plus 1, x minus 1, x plus 1. I'm going to do the sign chart back from what we learned in pre-calc 1. Our first interval is at x equals negative 1. Second interval is x equals negative or positive 1. This is the interval from negative infinity to negative 1, negative 1 to infinity, or negative 1 to 1, excuse me, and then from 1 to infinity. So I'm going to choose something in this first region. I'm going to say x is equal to, say, negative 5. When I put a negative 5, this is going to be positive. In fact, this one's going to be positive all along all of the intervals, so I'm just going to put plus everywhere. When I put a negative 5 here, this is negative. When I put a negative 5 for this one's negative, so the region is positive. Let's choose something in here. Let's choose x is equal to 0. So this is negative, this is positive, this region is negative. Let's choose something over here. Let's choose 10, so positive and positive, so this region is positive. Now, because I have to have this thing greater than or equal to 0, the domain for this function, my domain, is from negative infinity to negative 1 inclusive, union between 1 to infinity. So that's the domain. On my domain, I should have each one of these. The f of a existing, the limit as x approaches a, if f of x exists, and as x approaches a f of x equals f of a. So on my domain, that is going to be true, that between, when x is between non-inclusive of -1 and 1, it is discontinuous. And it's discontinuous because it's a jump. You have to physically pick up your pen and move it to another place, so this is a jump discontinuity. Okay, now let's take a look at f of t. Because this is the same thing as the cube root of t squared minus 1 raised to the 2, because it's a cube root, it is defined everywhere. So your domain on this one is -infinity to infinity. That means this is continuous everywhere. Okay, now let's take a look at our last one. We have the h of x is equal to the sine of x cosine of x. There's no place that sine is undefined on the real numbers. There's no place that cosine is undefined on the real numbers. And if you were to graph this, it would look something like this. So there's no place in which that's undefined anywhere, because sine of x and cosine of x is defined everywhere. So your domain on this is from -infinity to infinity. So it's continuous everywhere, just like g. All right, so let's take a look at the next example. My next example, we want to determine the intervals in which the following functions are continuous and then evaluate the given limits. Well, this one is continuous from 0 to infinity because the part that is having the issue is the square root of x. So because that is a place in which we are continuous from the right. Since we are continuous from the right, I can find the limit as x approaches 4 of f of x. So the limit as x approaches 4 of e raised to the x, I can do a direct substitution. So this is e raised to the square root of 4, which is just e squared. Similarly, the limit as x approaches 0 from the right, which we know is defined from the right, of e to the square root of x is, once again, we can do a direct substitution. This is e to the 0, in other words, 1. Let's take a look at b. So for b, we have the f of x is equal to the natural log of x. So for the first top piece, we know the domain for the top piece is from 0 to infinity. The sine, the sine inverse, its domain is from -pi/2 to pi/2. Now let's combine these together. When we combine these together, is that the domain of f of x, so I'm going to take these two together and say what is the domain. The domain for f of x is, at the very minimum, it has to be 0, but non-inclusive. So it is going to be from 0 to pi/2 inclusive. So that is the domain of my function. So then I ask myself, is 1 in there? And the answer is yes. Pi/2 is less than 1. So the limit as x approaches 1 from the left will be the natural log of x over the sine inverse of x. So I just want to make sure that my calculator is in radians. And so I can do a direct substitution. The limit of, the natural log of 1 is 0. And then the sine inverse of 1 is 1.57 radians, and so my answer is 0. Let's take a look at this example in which we're asked to sketch a graph with this information. So first of all, the domain is everything. It has an infinite discontinuity at -6. At -6, the output is 3. The limit from the left and the right of -3 is the same, so it does exist. It is 2. At f of -3, though, it is 3. F is left continuous but not right continuous at 3. The limit as x approaches -infinity of f of x is -infinity, and the limit as x approaches positive infinity is positive infinity. So let's go ahead and start graphing all that we know. So one of the things that I know is something's happening at -6. So here's -6. Something else is happening at -3. So here's a -3. Something is happening at 3. So here's 3. Okay. So f has an infinite discontinuity at -6. All right, so at -6, that tells me I'm going to positive or negative infinity or both. I also know as x goes to negative infinity, it is going down. So let's do this. On the left side of -6, I go up, but then I'm going to come down, and then my graph is going to go down. So this satisfies this part, and it satisfies the infinite discontinuity, at least on one side. Also at f of x, it equals -3. So f of -6 is -3. So let's put this at -3. And then at -3, it is 3. So here's another point that I've got to have. As we approach x from the left side of -3, and as we approach x from the right side of 3, it is 2. So this is 3, here's 2. So I have an open dot. It's going to approach it. It's going to be 2 from the left. It's going to be 2 from the right. So here we go. It goes somewhere. I have to figure out where it goes, and the way I'm going to figure out where it goes is it is left but not right continuous at 3. So at 3, it is left, so it has to have a dot there. So maybe it's going to go look like this. It is not right continuous at 3, so maybe, because they didn't tell us anything else, there's 3. There's the right side. And it may look something like this. So now we go back to see if we've hit every single part. So, starting at the very top, is there any place in which my domain is not defined? And the answer is no, because as I read my graph from negative infinity to infinity, even though it's not defined, because we have an infinite discontinuity at 6. See how it goes up infinitely? So let me put my arrow on there. It is defined at, it is defined here. This is only one way I've done. I could have done it this way as well. And so I could have said, hey, let's have my graph look like this. And if I have my graph look like that, then all I have to do then is just make sure that, let me erase this. There we go. Then all I have to do is just make sure that I have a point, this ordered pair point, which is -6 comma negative, or what is it? -6 should be, it should be +3. So at -6 I have +3, so I need to move this anyways. So at this I have a +3. So we have that ordered pair right there. This is the ordered pair, -6 and 3. That's that ordered pair right there. All right, so now I've got that one. I've got an infinite discontinuity. I've got it going from negative infinity to infinity. At x, as x approaches -3 from the left, and as x approaches -3 from the right, it exists, and it is 2. So that's this part. So that is this part. At f of -3, it is 3. So that's that ordered pair right there. The ordered pair, which is -3 comma 3. So I've taken care of that one. taking care of that one. It is left continuous at 3, but not right continuous. That takes care of that. And then as x approaches negative infinity, it is negative infinity. As x approaches positive infinity, it is positive infinity. This is just one example that satisfies all of that. It is not the only one. So if you did one that's slightly different, cool. Okay, so now we're going to move on to the intermediate value theorem. Before attempting to find any x that satisfy the solution, it is worthwhile to determine whether or not the solutions exist. Suppose f is continuous on the interval from a to b, so it's a closed interval. Closed just means we include the endpoints. And L is the number between f of a and f of b. Then there is at least one number c, so that f of c is equal to L. So let's take a look at these two graphs. So here is A, here is B, C is somewhere in there. Here's f of A, here's f of B. This somewhere in between f of C is the output L. Similarly, here's A, here's B. This one actually has multiple places in which I have an output that is L. So as an example, a particle moves along a line, has each time t is a position of the function s of t is continuous. Assume at 2 seconds the position is 5, and at 5 seconds the position is 2. Another particle moves such that its position is given by h of t is equal to s of t minus t. Explain why there must be a value c between 2 and 5 such that h of c is equal to 0. So we know, so I'm just going to do a quick little sketch here, that s of 2 is 5. We also know at s of 5, the output is 2. So what we know is the graph has some shape. Who knows what the shape is? But I do know it's continuous from left to right. And this is my function s of t. Now, s of t is a continuous function. H of t is going to be s of t minus t. So h of t is going to be s of t minus t. Now, there has to be some value c within there so that h of c is equal to 0. As an example, say that this is 3, right? And let's assume, this is just assumption, that this is the ordered pair 3, 2. Now, to satisfy this, h of 3, I wrote f, h of 3 we can see is s of 3 minus 3. That means h of s of 3, which we said was 2 minus 3, is equal to negative 1. Now, we've now crossed the x-axis. But if I look at h of 2, this is going to be s of 2 minus 2. S of 2 happens to be 5, minus 2 happens to be 3. So what we know, because this is a continuous function, h of t must be a continuous function, because it's defined as a continuous function minus a real number, so it's going to be continuous. Because I have one output that is positive, one output is negative, we had to have crossed the x-axis or the t-axis somewhere along there. That's why there must be some value c. And even if I don't have any other values except for h of 2 and h of 5, s of 5 minus 5 is going to be 2 minus 5, which is negative 3. Now we know from our pre-calc 1 that when I have an output that is 3, a positive number, and an output that is a negative number, and it's a continuous function, it had to have crossed the x-axis somewhere, and wherever that crosses, we call it C. That means 8 of C must have hit the x-axis somewhere, and C is the place in which it crosses. So you're shopping for a $150,000 30-year mortgage loan to buy a condominium. The payment M of R is defined here. The annual R is the annual interest rate. Suppose banks are currently offering annual interest rates between 3 and 4. Use the intermediate value theorem to show there is a value of R between 3 and 4% and interest rates between 3 and 4% that allows you to make monthly payments of $675. So the way that you do that is you plug in the first point, so M of 0.03, and you have 150,000, and then 0.03 divided by 12 over 1 minus 1 plus 0.03 divided by 12 raised to the negative 360. And we get $632.41. So now let's do this again, but with 4%. So M of 0.04 is 150,000. 0.04 divided by 12 over 1 minus 1 plus 0.04 divided by 12 raised to the negative 360, and we get $716.12. Because this is a continuous function, that there has to be somewhere in there has to be an interest rate that's going to give me a mortgage of $675. And the interest rate, the way I'd figure that out is I'd write 675 is equal to 150,000. R divided by 12, 1 minus 1 plus R divided by 12 raised to the negative 360, and then I'd use my regular algebra skills and to solve for R, and then that's it.